For me to be here for the first time in Cambridge at the Newton Institute, and I will talk to you about the classification of a family of type 3 factors, and that's a joint work that I did with Cyril Houdayer and Dimitri Shlyakhtenko. And if I have time towards the end, I will also talk about more structural properties of these factors that came from a joint work with Remy and Boutonnet and Cyril. Now, I don't assume that everybody is familiar with type 3 factors, and especially this class, so it will be a quite introductory talk, especially in the beginning. So what will this be about? What Shlyakhtenko did was to construct a kind of functorial family of von Neumann algebras, and before giving you the more formal definition, let me show you a few of these functorial properties to give you some intuition for these factors. So the initial data will be an orthogonal representation of the real line. So just orthogonal one parameter group of orthogonal operators on a real Hilbert space. And we will associate to that a von Neumann algebra equipped with a faithful normal state. Now here are the functorial properties. If you take the direct sum of two representations, what will come out is the free product, in the sense of Voiculescu, the free product of the two resulting von Neumann algebras with respect to these favorite states that they come with. The other functorial property, say on the level of morphisms, is that when you have a contractive intertwiner between two orthogonal representations u and v, they canonically give rise to a completely positive map theta, preserving the favorite states phi and psi. So somehow it's like a functor from orthogonal representations with contractive intertwiners to von Neumann algebras with favorite states, where the intertwiners are really the completely positive maps. Okay, now as you can see, if you would replace in this thing free product by, say, certain types of tensor product, symmetric or anti-symmetric, then you will recognize that this is really a kind of free analog of canonical anti-commutation relations, and that's one way to think of this, as a free probability analog of the Carr functor. Now, yes?
Does it make sense to ask what is the value if I take the representation to be one-dimensional?
Yes, and I will show you in a minute, but it's not very spectacular. If you take this to be one-dimensional, so that it must be the identical representation, you will just get L infinity of 0, 1, a diffuse abelian von Neumann algebra. So actually, this already was a generalization of another free functor, the free Gaussian functor of Voiculescu, and that's what I will first explain to you. Now, the whole thing is we associate such a von Neumann algebra with the state to any orthogonal representation, and we would like to classify this family of von Neumann algebras in terms of these orthogonal representations. Okay, so what's the original construction of Voiculescu? So the starting point is a Hilbert space H, and then you perform the full Fock space construction. So omega is called the vacuum vector. It's, say, a canonical one-dimensional subspace, and then you take orthogonal direct sum with all tensor powers of H. And as many of you know, and as we have seen, by the way, also in last week in Roberto Longo's lectures, you then get the so-called left creation operator, although he took antisymmetric tensor product, but let's take symmetric, the full tensor powers here. So the left creation operator on the full Fock space is defined by sending the vacuum vector to xi, and then a tensor product of xi1 to xi(n), you just put the xi in front of this. Then there is also a favorite state on operators on the full Fock space, namely the vector state given by the vacuum vector, called the vacuum state on these bounded operators. And the basic theorem that Voiculescu discovered is the following one. So it consists of 3 points. The first one is if you take a single vector xi and you consider this self-adjoint operator, the real part of the left creation operator, you can consider the distribution of this operator with respect to the vacuum state. So you can compute the vacuum state on all powers of this operator. That will correspond to a probability measure on the spectrum of that self-adjoint operator, and what he could compute is that this probability measure is exactly Wigner's semicircular law, so the semicircular law on the radius that you expect twice the norm of psi.
What
do you get for the CAR? Ordinary CAR?
I don't know by heart. Is that the one where you get Gaussian or no?
2-point masses. It's finite dimensional. 2-point masses. One minus one plus one.
Okay. 2-point masses.
Oh, really? Okay.
So that's one basic observation. So already here that answers your question, because if there is only one vector around, what you see is what you get is the von Neumann algebra generated by this single self-adjoint operator, as we will see, a single self-adjoint operator whose distribution is a non-atomic measure, the semicircular measure, and that creates you a copy of L infinity of the interval 0, 1. Okay. Then the second absolutely crucial observation is that if psi and eta are orthogonal vectors, then the corresponding self-adjoint operators with respect to the vacuum state phi are free in the sense of Voiculescu. So that's the other absolutely crucial observation. And as a consequence of this, if I take n orthonormal vectors, E1 to En, say the standard basis for Cn, what you notice then is that these n self-adjoint operators, each of them has a diffuse distribution with respect to phi. They are free with respect to phi, so together they generate a copy of the free group factor L of Fn, because it's a free product of n diffuse abelian von Neumann algebras. So the striking thing is that we now have a functorial construction to associate to a Hilbert space and its basis for the moment, a copy of the free group factor, and already you get something that you would not get from the first image of the free group factor, namely that the orthogonal group On very naturally is acting on the free group factor. That's something you would not have immediately from generators and relations in, or no relations in L of Fn. Okay, so this is the starting point. Now, the starting point here is you have the n-dimensional Hilbert space and its orthonormal basis. So you can generalize this vastly, and also that came up in Roberto Longo's lectures last week. Namely, take any situation where H is a Hilbert space and K is a closed real subspace, and it will be a standard subspace. That was the word that Roberto used. So the two basic assumptions are that the real Hilbert space intersected with I times the space is the zero vector, and the real space plus I times K should be dense in H. So let's take this as basic data and think as an example of Cn here and the standard basis, and then K the real linear combinations of the basis vectors. Yeah? Okay. Now with that data you can construct a von Neumann algebra, namely the von Neumann algebra generated by all these real parts of creation operators where you create by real vectors psi, and you make them act on the full Fock space as before. And then the vacuum state that we have seen is automatically a faithful state on this von Neumann algebra. It's called the free quasi-free state. And the basic question I can now reformulate in a more precise sense and say that we want to classify these von Neumann algebras coming out of these standard inclusions of a real Hilbert space in a complex Hilbert space. Now, let me now explain what's the link with orthogonal representations to reformulate a bit the thing. So that's very classical. We have seen that last week as well. So how can you construct such standard inclusions of a real Hilbert space in a complex Hilbert space? Well, they are exactly parameterized by the orthogonal representations of the real line. So in one direction, if you start with an orthogonal representation, what you build is first the complexification of the carrier Hilbert space HR. That complexification comes with, of course, an anti-unitary conjugacy like this, and the orthogonal representation complexifies to a unitary representation on H. That's all canonical. Now, this means that now UT has become a one-parameter group of unitary operators on H, so it has a generator. It is delta to the power IT for a self-adjoint positive operator, delta on H. Now with that, I can define a real subspace, because with that unbounded operator delta, now comes this new involution. So on H I can define this operator J delta 1/2. It will be an involution, unbounded, but closed, and therefore this is a closed real subspace of HR, of H, and it's in this standard position. So you do have these two properties. So this means that now I can say that associated to any orthogonal representation, I have such an inclusion of a real subspace in a complex Hilbert space. And moreover, as I will indicate in a minute, any such standard inclusion arises in this way for a canonical orthogonal representation. So the new notation becomes the von Neumann algebra generated by this inclusion. I will now denote as gamma of UHR. I mean, it's generated or given by the unitary, the orthogonal representation and the Hilbert space HR. So to do the converse, by the way, if I have such a standard inclusion, so these two properties, how to get an orthogonal representation? Well, one shows that this operator, that's densely defined on Kr plus IKR, it's automatically closed because Kr is a closed subspace, and then you can do polar decomposition and you can use delta to generate a one parameter group of unitaries, and you can construct HR and go back. Yeah? Okay. So now we are in the situation that to any orthogonal representation is associated a von Neumann algebra, and we want to classify these. Okay, so the first thing, since this is a von Neumann algebra that comes with its favorite free quasi-free state, let's take a look at cons in modular invariance coming with this state phi. So maybe just 1 second for those who have not seen modular theory, but I will be extremely brief on that. So given the state phi on M, there is the so-called modular automorphism group. So these are automorphisms of M, and they replace somehow the lack of triviality. So the modular automorphism group would be trivial if phi would be a trace, then it's just the identity, and otherwise if you do the right kind of analytic continuation, you see that on densely defined subalgebras, you can see how the lack of triviality is covered by the modular automorphism group. So it's a canonical one parameter group of automorphisms that comes with any fateful state. So that's Tomita Takazaki theory. And here you can very easily compute it. So if I take this as a basic generator of my free Araki-Woods factor, then the modular automorphism group acts on it in the way as the unitary one parameter group was acting on the vector. Yeah? So that's not a surprise. So the basic results that Dima, after defining these objects, could prove on these factors are the following. So there is one exceptional case, so the one that you were asking. In the one-dimensional case, you get an abelian von Neumann algebra, L infinity of 0, 1. And in all other cases, you get a factor. And you can exactly say what's the type of this factor. So it is of type 2, 1 exactly only when we had the trivial representation of a certain dimension. And it's of type 3 lambda exactly when the representation is periodic with this period. And it's type 3, 1 basically in all cases, because once the representation is not periodic, you get a type 3, 1 factor. So really this is a family of type 3, 1 factors that we are interested in.
You never get 3, 0.
No, you never get 3, 0. And the reason is that these factors are automatically full. So if you look at the automorphism group of M, the inner automorphisms, so those implemented by a unitary of the algebra, are automatically a closed subgroup of the full automorphism group in this case. And by the way, that connects me here. The modular automorphism group, it depends on the choice of the state, but by Kahn's theorem, if I view this as a map from the real line to automorphisms divided by inner automorphisms, that's canonical. Because if I change the state and the modular automorphism group changes by an inner perturbation by Kahn's co-cycle theorem, so the map from the modular map to the outer automorphism group is a canonical one. And moreover, in this case, since the inner automorphism is always closed, this outer automorphism group is a nice Polish group, so we have a good structure over there. Why am I saying this? Because the finest modular invariant that Kahn introduced, covering all of the 3 lambda, 3, 1, etc. classification, is for full factors. indeed full factors, so those factors where this is really a nice Polish group, you can define the so-called tau invariant. And the tau invariant of Kohn, it's a topology on the real line, namely the topology on the real line, that's exactly the weakest topology that makes this homomorphism continuous. So it's a topology on the real line, and you can compute it. So for these factors, they are what you expect them to be. It's the same as the topology induced by the original orthogonal representation. Yeah? So everything stays canonical in this way. But this is an important remark because there is a special class, the special class of almost periodic representations. So the representations that are sums, direct sums of finite dimensional representations. In this case, two-dimensional then, yeah, because it's the real line that's acting orthogonally. So the almost periodic case, that's exactly the case where this is, by definition, a sum of finite dimensional representations. Now, how can you recognize that from this topology? You can recognize that from the topology as being a compact topology, a compact group topology, that the completion is compact. That's exactly the diagonalizable case, the almost periodic case. And indeed, as I will show you on the next slide, in the almost periodic case, Kohn introduced another invariant, the so-called SD invariant. The SD invariant is a subgroup of the positive real line. I will define it in a minute. And what Dima could also show is that the factor is almost periodic, even only if the representation is almost periodic. And then the SD invariant of Kohn is exactly the subgroup of R plus generated by the eigenvalues of Phi. What are, if you wish, ut is delta to the it. I really mean eigenvalues of this operator delta. Okay, so what are these almost periodic factors? So we would say that a factor is almost periodic if it admits an almost periodic state. So there are different ways to say when a state is almost periodic. Well, when constructing the modular automorphism group, as you remember, there is also these modular operators on L2 of M, and the state is almost periodic precisely when the modular operator delta phi is diagonalizable. Yeah. Okay, so that's the almost periodic case. And once you have one almost periodic state, you can look at the eigenvalues of that modular operator, but that's not canonical because there might be many almost periodic states. So somehow you have to take the intersection of all possible eigenvalues, and that's Kohn's SD invariant for an almost periodic 3-1 factor. Now you can also say it slightly more conceptually, because another way to say what's almost periodic is saying that the closure of this map is a compact subgroup here. So it's a compact abelian subgroup here. It's an embedding of R into a compact abelian subgroup, and then dualizing, you really get an accountable subgroup SD of M in R star plus. Okay, so that's SD invariant for full type 3 factors that are almost periodic. And then the totally surprising theorem that Shlyakhtenko proved in '96 is that in the almost periodic case we have a complete classification theorem. So the free Araki-Woods factors in the almost periodic case are completely classified by their SD invariant as a subgroup of the positive real line. Okay, so that's the statement once more. Now, here there is a little attention. There is only one case you have to exclude. You cannot speak about the trivial representation, because then we know, if you take the trivial representation, that you get a free group factor with its number of generators the dimension of the Hilbert space. So that's, of course, not covered by the theorem, but it does show that the theorem is quite surprising, that just beyond that, in the almost periodic case, you do have a full classification theorem. Now, the hard part is, of course, the isomorphism direction, because the invariant was already there. The invariant is Kohn's invariant. But then I have to show you that given two orthogonal representations whose eigenvalues happen to generate the same subgroup of R plus, so the sets of eigenvalues are not equal, they just generate the same subgroup of R plus, that then there is an isomorphism of the factors, and that's by a very smart set of matrix models for these operators that Dima could prove this. And now I come to the main question, how to go beyond the almost periodic case. But maybe one thing to close off, of course it also shows that in type 3 lambda there is exactly one free Araki-Woods factor, because that's exactly the case where SD is just given by the powers of a lambda, the only case where you have a closed subgroup of R star plus. Yeah? Okay. So how to go beyond the almost periodic case? Well, until recently there were only a number of, say, qualitative results. I mean, there were no new quantitative invariants for these factors. And most of the qualitative results that I will quote now were based on the following type of invariant, if I may say so. It's an invariant that you associate to any type 3 factor, namely its continuous score. So if you make the cross product with a modular automorphism group, what you get is a to infinity von Neumann algebra with a semi-finite trace. In the 3-1 case, you get a to infinity factor by the Kohn-Takazaki construction. Now, the type of results that were proved is the following, for instance. Dima proved that when you take as orthogonal representation a multiple of the regular one, then the continuous score is an amplification of the free group factor, the infinite amplification of the free group factor, while for other types of orthogonal representations, you could prove that the core cannot be like this. So you can distinguish between families, but it's not a true classification theorem. For instance, what is a case where you can say that you don't have a free group factor as a continuous score? If all tensor powers of the representation are disjoint from the regular representation, it could be shown that the continuous score can never be a free group factor. Then Shlyakhtenko could also produce two non-isomorphic free Araki-Woods factors that have the same tau invariant. That was the finest kind of invariant you can extract from modular theory. So modular theory will never be enough to really distinguish between all free Araki-Woods factors. And here is another result that's at the same time more general but also a bit weaker than what Shlyakhtenko proved here. When you use a mixing representation, so meaning that all matrix coefficients of the representations are functions that tend to 0 at infinity, if U is a mixing representation, then the continuous score is solid. That's a property we will come to at the end. These are examples of solid von Neumann algebras. And then for other types of representations, the core cannot be solid. So again, you have this kind of distinguishing between families of examples rather than classification. And then here, this result could be improved by Ben Hayes. Actually, it's enough to assume that U itself is disjoint from the regular representation to get that the continuous score cannot be an amplification of the free group factor. Okay. Now, what I want to show you now and discuss now is a new classification theorem that's really a classification theorem. Now, let me first very quickly review how to parameterize orthogonal representations just by their spectral data. So I'm sure that you all know about this, but let me do it quickly. So how to describe orthogonal representations of the real line through their spectral data? Well, given any symmetric Borel measure on the real line, you build the following real Hilbert space on which you have a canonical orthogonal representation. And as you know, any orthogonal representation is isomorphic with a direct sum of a number of these, and that allows you to completely classify orthogonal representations in terms of a symmetric measure on the real line and a multiplicity function. So the multiplicity function, of course, you assume that it's bigger than 1 almost everywhere, and then it's not really the measure that's the classifying thing, it's really the measure class that's classifying the thing, because two orthogonal representations will be isomorphic if and only if their corresponding spectral measures are absolutely continuous, so define the same null sets, and the multiplicity functions are equal almost everywhere. So the spectral data, it's really a measure class and a multiplicity function. So from now on, we could also write as a free Araki-Woods factor the one associated to such a symmetric measure class and a multiplicity function. Yeah? And then to understand the following slides, it's good to know that the spectral measure that goes with the tensor product representation is the convolution of the two probability measures, yeah? Because convolutions will show up in a minute, and that's quite natural because of this, yeah? And the other thing to keep in mind is, so what is the almost periodic case corresponding to? The almost periodic case is, of course, exactly corresponding to the situation where this measure is atomic, purely atomic. So that's the almost periodic situation. Okay, so here is the classification theorem. So it will not be valid for arbitrary free Araki-Woods factors, so we cannot classify all of them right now, but we can do it for a quite large class of orthogonal representations. And here is the class of probability measures for which it works. So we will be looking at measures that have, as all measures, a continuous part and an atomic part. And then the assumptions are the following. The continuous part should satisfy this type of property. So if I convolve the measure with itself, it's absolutely continuous with respect to mu. Another way to say that is that the tensor product of u tensor u is contained in a multiple of u itself. And then there is an assumption that may sound unnatural now, but that will be very natural in a minute. We do need a little bit of atomic part. So we need at least an atom outside 0. So we need just an atom somewhere and a continuous part with this property. Well, in that case, there is a full classification, and the full classification will be by two invariants. First of all, an invariant that we may recognize from the almost periodic case, namely the subgroup generated by the atoms. Remember, the subgroup generated by the atoms, that was what was the SD invariant in the almost periodic case. So it's quite natural that it shows up again. The subgroup generated by the atoms, and then secondly, a measure. So if I take measures from this class, the associated free Araki-Woods factors are precisely classified by this subgroup of the real line and by a measure class. And what's the notation here? I denote by this any probability measure which is atomic and with atoms exactly in this subgroup of R, and then I take convolution. So another way to say this is that this convolution is the join of all. So you take an atom or anything in the group generated by the atoms, and then you translate mu c. Because taking convolution with an atomic measure is not so difficult to do. It's like translating the measure over all possible atoms. So the invariant is the following. You started with the measure class mu c, but then I have to translate this measure class by all possible atoms that I had in mu a, and all elements in the group generated by these atoms. Yeah. So that's the invariant. The measure class, this continuous measure class, and this, if you wish, discrete measure class, namely this subgroup of R. Okay, now you may wonder how large this family of measures is. Is it easy to come up with measures that have this property? Yes, there are tons of measures that have this property, because starting with any continuous measure mu 0, you can like stabilize it. So if I start with any continuous measure mu 0, I can join all its tensor powers, and then I do get a measure that's in this class. And I can start with any mu 0, and then I just add a few atoms. And all of these work, so therefore there is indeed a huge supply of non-isomorphic free Araki-Woods factors that have complete the same invariance and everything, yeah? But it's not a full classification theorem.
You can't say anything if you don't add atoms?
Exactly, and on the next slide it will become clear why. Because this may sound like an almost ad hoc theorem, and it's a little bit of an ad hoc theorem, but the following one is a very conceptual theorem. So there is a very conceptual theorem behind, and this is about states with a large centralizer. So what is the centralizer of a state? It consists of, it's a subalgebra, the sub-von Neumann algebra, of those elements on which the state is behaving like a trace. The same thing is saying that it's invariant under the modular automorphism group, yeah? Okay. So what's the true theorem? The true theorem is about arbitrary free Araki-Woods factors. So the theorem is take any free Araki-Woods factor and take on that free Araki-Woods factor any fateful state with a non-amenable centralizer. Then the point is that basically it must be the free quasi-free state. So the conclusion, and I will specify in a minute what everything means, the conclusion then is that roughly the state must be unitarily conjugate to the free quasi-free state. So once a state has a non-amenable centralizer, it must be the free quasi-free state up to unitary conjugacy, except that it's not exactly unitary conjugacy. So it's conjugacy by a partial isometry on corners of the algebra, so in the best possible way. So you have a projection centralizing phi, you have a projection centralizing psi, you have a partial isometry connecting the two, and then you have the relation that under this partial isometry you have conjugacy of the two states. Okay, but think of this as unitary conjugacy of the two states.
Sort of like Morita equivalent?
Yes, exactly. Now another thing to see is that it could be that the free quasi-free state even has a trivial centralizer. So what is the theorem then saying? That there are no states with a non-amenable centralizer, because they should then be unitary conjugacy with unitarily conjugate with a free quasi-free state who hasn't a non-amenable centralizer. Yeah? Okay. So the special thing is that on a free Araki-Woods factor, the only way a state can have a non-amenable centralizer is because it's the free quasi-free state. And now comes up the assumption on the non-trivial atom. When does the free quasi-free state itself has a non-amenable centralizer? Roughly exactly in the case where there is at least one atom. Now, what can we then conclude? Well, if you have an isomorphism between two free Araki-Woods factors, where one of them happens to have an atom, then by the theorem, you find an isomorphism that's state preserving. When I talk about isomorphism of a Neumann algebras, I'm not supposing that they are preserving the states, yeah? But here you get it then for free, because on one side you have a non-amenable centralizer, and on the other side you have a free Araki-Woods factor, so it must be the same state. Now, once there is a state preserving isomorphism, then the modular data must be isomorphic. And the modular data is given by this measure class. So that's totally true in general. The spectral measure of the modular operator of the free quasi-free state is given by this convolution, the join of all convolution powers. So therefore, in the specific case where we were, you can just compute this, and this reduces to the type of things that we were saying. Yeah? Okay. So that's the main theorem, that non-amenable centralizer can only happen with the free quasi-free state. Let me connect this to a very interesting open problem known as the Kohn bicentralizer problem that I want to advertise once more. So the question that Alain Kohn was asking is, does every 3-1 factor have a trivial bicentralizer? Now I will not explain the original definition of bicentralizer, but an equivalent version of it. But let me first say that what Houdayer proved is that the answer is yes for the hyperfinite 3-1 factor, and that was really the key point in proving uniqueness of the hyperfinite 3-1 factor. That's the reason why Kohn left open the 3-1 case, because he knew that with an answer yes to the bicentralizer problem, there was uniqueness, and Houdayer solved this very hard bicentralizer problem. Now, Houdayer also gave a reformulation of the bicentralizer problem, and it's a very innocent looking statement. It's just asking whether on any type 3-1 factor you can find a state such that the centralizer is large in the sense that it has trivial relative commutant. Anything in M commuting with a centralizer should be a multiple of 1. Well, and then, by the way, automatically, but that's not so hard to see, the set of states for which this holds is dense. There are many states with that property then. Now, on the other hand, what we show is that, for instance, if mu is a non-atomic measure, is a purely continuous measure, then every fateful normal state has a small centralizer, in the sense that the centralizer is amenable. But yet, on the other hand, already before, Cyril Houdayer showed that free Araki-Woods factors do satisfy Kahn's bicentralizer problem. So we are in the following very subtle situation. On free Araki-Woods factors built with a continuous measure, for instance with the Lebesgue measure, what you have is that all states have a small centralizer in the sense of being amenable, but there are states with a large centralizer in the sense of having trivial relative commutant. Of course, that's not a contradiction. Yeah, there can be a hyperfinite to one factor sitting inside with trivial relative commutant. We cannot construct it by explicit means, no way. But it is there. Yeah. Okay. Now, let me discuss a few other questions. I should have stressed that when I showed you the classification theorem, the classification theorem in our case was independent of the multiplicity function. So already in Dimas' almost periodic case, the multiplicity didn't matter. Also in our case, multiplicity doesn't matter. Now in general, it's clear that multiplicity should be tricky, because if I take with multiplicity m the trivial representation, so the measure concentrated in 0, then you get a free group factor. But also beyond this for the moment undecidable case, if I take the Lebesgue measure and I add an atom in 0, when I take it with multiplicity 1 or multiplicity 2, I get non-isomorphic factors. And why is this true? Because on the one hand, what follows is that for this factor falls under our theorem saying that all centralizers are amenable, while this one has the free quasi-free state with a non-amenable centralizer. So they can never be isomorphic for this kind of qualitative reason. So the multiplicity function in general matters, and it shows you how delicate it will be if you ever want to try to formulate a complete classification theorem, yeah, because you will have to deal with these cases as well. So we are not even guessing what the complete invariant would be. Yeah? Here is another funny open case that follows from our results. So one thing that follows is if you take Lebesgue measure with infinite multiplicity and you join the atom at 0 with multiplicity m, you all the time get the same 3-1 factor, and then you come at m infinity, and whether or not you still get the same is equivalent with the free group factor problem. So again, it shows you how delicate it will be to make any general guess on the full classification of these factors. Yeah? Let me also quote a few quite intriguing open cases. Take as a symmetric measure Lebesgue measure on the interval minus a to a. We have no clue at all whether this depends on the size of the interval or not. The same, we already quoted this example. If I remove again the atom in 0, so Lebesgue measure or Lebesgue measure plus an atom in 0, we don't know whether they're isomorphic, but there are a few, say, contradictory things. On the one hand, they have the same continuous score, namely the amplification of the free group factor, that's null. But on the other hand, it's clear that there cannot be a state-preserving isomorphism, because here the free quasi-free state has trivial centralizer, here the free quasi-free state has a diffuse abelian centralizer. So no state-preserving isomorphism, but maybe there are other isomorphisms. Now, what is really behind, and what I want to stress now, is our conclusion, our main theorem was that under certain conditions, two states on the free Araki-Woods factors are unitarily conjugate. Now, in general, that's extremely hard. If two states on a von Neumann algebra are given, to decide whether or not they are unitarily conjugate, we had very few tools in hand up to now. Now, what I want to show is that what we developed is actually a tool that fits within Sorin-Popa's deformation rigidity theory, and that has as a conclusion unitary conjugacy of states. So here is the criterion, and this is totally general. So you take an arbitrary von Neumann algebra, you take two faithful normal states, and we will study when are these states unitarily conjugate. Now, I'm saying unitarily conjugate, but you should take this with the same grain of salt as before. it's actually conjugate with an isometry and under the same thing, projection here and there. Yeah. But think of unitary conjugacy, but the true thing one can look at is this, yeah? Okay. Now here is the criterion. If I give you two states, two different faithful states, then they have different modular automorphism groups. So a priori they have different continuous scores, cross products with the modular automorphism groups. But Kohn showed by the co-cycle theorem that these are canonically isomorphic. So if I change the state, there is a canonical isomorphism between the two continuous scores. This canonical isomorphism is acting as the identity map on M, but it's not acting as the identity map on R. So this means that you can think of this continuous score as something that's abstractly there, and for every state, it contains a copy of the group algebra of R. That's another way to view the same thing, yeah? So for every state on the algebra, we get a group algebra of R sitting as a subalgebra in this single abstract continuous score. Now the criterion that we showed is that unitary conjugacy up to this and that of phi and psi is the same as what Popper calls intertwining by modules for these subalgebras. So towards the very end of Sorin's lecture on Monday, he said that one of the several crucial tools in deformation rigidity theory is this concept of intertwining by modules, and it holds between two such realizations of the group algebra of R inside the core, even only if the states are unitarily conjugate up to up to projections. Now why is this good to have? Because within deformation rigidity theory, we now have plenty of tools to decide whether or not such a thing holds in a concrete situation. So it's much harder to come up in a concrete situation with explicit unitaries intertwining two things. But this is a checkable thing, mainly because of criteria that Sorin developed to check such a intertwining relation.
What about this lambda?
A lambda. Where is a lambda? Yes. So you could predict that. I mean, intertwining by modules is, as the word says, given by a bimodule, and it's related to how left and right dimension of the bimodule somehow relate, yeah? And that need not be by one, yeah? That's roughly what it comes from. Okay. Now, before going a bit further into that, let me show a few other applications to certain free product constructions. So let me now start all the way with a continuous measure, say the Lebesgue measure, with infinite multiplicity, and take the corresponding free Araki-Woods factor. Okay. So one other consequence of our theorem is that you can classify free products with M. So if you take non-amenable 2-1 factors with their unique trace, then the free product with this single M is isomorphic with the other free product, even only if not isomorphism of A and B, but exactly isomorphism of A with an amplification of B, these amplifications that came up in the talk of Yusuke Ezono on fundamental groups, because that's exactly how fundamental groups of 2-1 factors are defined. Now, why is this relation important? Well, yeah, again, here, of course, when I say isomorphism, isomorphisms are not assumed to be state preserving, and the whole thing is that by the theory, you deduce that after the existence of an isomorphism, there also is the existence of a state preserving isomorphism. Yeah? Now, why is this interesting? Because digging deeper into these free products, we could negate the following kind of conjecture that was made. So let me first say what was done in the tracial case. So by work of Dijkma and several other people, if you take a free product of amenable von Neumann algebras with a trace, so injective tracial von Neumann algebras, you take a free product, what you get is essentially a free group factor, always. An interpolated free group factor to be correct. From there, one could guess that if you take a free product of arbitrary amenable von Neumann algebras, that what you should get is a free Araki-Woods factor, because that should be the analogy. But no, I mean, using these techniques, you also get many free products of amenable von Neumann algebras, for which you can prove that they cannot be free Araki-Woods factors, yeah, that they are beyond this class. Okay, so in the remaining 5 to 10 minutes, let me discuss another property, another structural property of free Araki-Woods factors. I already mentioned the word solidity.
Sorry, in a second, what is the invariant that allows you to conclude this, like these last two lines?
Yes, I can tell you that. So the point is the following. In certain cases, assume that you have a free product isomorphic with a free Araki-Woods. Now, you could take situations where both phi and psi have certain centralizers, yeah? You can take situations like that. Therefore, the isomorphism would force the existence of the isomorphism would also force the existence of a state-preserving isomorphism. Now, being a bit more careful, there are situations where you can show that a free Araki-Woods factor cannot have an amenable subalgebra that's globally invariant under the modular automorphism group of the free quasi-free state. Now, to be very correct, if you take a free Araki-Woods factor, it's always, as a representation, you have the sum of the atomic part and the continuous part. And what you show is that any amenable subalgebra globally invariant under the free quasi-free state must sit in this almost periodic part. So if you make sure that here it's really not almost periodic, then you get a contradiction. Well, that's very roughly the argument. Okay, let's turn towards solidity. The common theme for a while was that free Araki-Woods factors really are, say, type 3 versions of free group factors, and therefore they should have all the properties that free group factors have. And that was indeed done, so let me show a few of the properties that free group factors have. The first very striking application of free probability theory was given by Voiculescu, who could show that the free group factors, they don't have a Cartan subalgebra. In a minute I will tell you what is a Cartan subalgebra. But first let me say that Ozawa proved that free group factors are solid. So what does it mean to be solid? It means that if I take a diffuse subalgebra, then its commutant must be amenable. So inside, diffuse means no minimal projections. So inside the free group factor, there is no place for something diffuse to commute with something non-amenable. There is just no place for that. Now, what is a Cartan subalgebra? Well, assume that A in M is a maximal abelian subalgebra whose normalizer, and what is the normalizer? It's the group of unitaries normalizing. So that came up in Sorin's talk. Whose normalizer is generating the entire von Neumann algebra. So Cartan means A in M Cartan means a massa, maximal abelian, and the normalizer generates everything. That's equivalent to saying that your algebra is realized as the one coming from an equivalence relation and a Tukos cycle, by the way. So Voiculescu could prove that that doesn't exist in the free group factor, and then Ozawa and Popa could hugely strengthen this statement because they could show that when you take any diffuse amenable subalgebra, for instance a massa, then its normalizer is not only not the entire algebra, no, it must stay amenable. So it's very far from being the entire algebra. That property was then coined strong solidity because it's a strict strengthening of solidity. And then since free Araki-Woods factors really are type 3 versions of free group factors, the same properties were shown for them. So Shlyakhtenko proved that they are solid. Houdayer and Ricard showed that they have no Cartan subalgebra. But this one was more difficult to settle. Now, if I say that they are solid and have no Cartan, we should give definitions of solidity and Cartan subalgebras for type 3 factors, and you just copy the definitions in the 2-1 case, except that from the beginning, you only look at subalgebras that are the range of a conditional expectation. Because otherwise you can do normal conditional expectation. Because otherwise you can do, of course, silly things. As you know, a type 3 factor is isomorphic to its tensor product with B of H. So you will not just take any von Neumann algebra in B of H. I mean, that's a silly thing to do. Now, in about a year ago, what Rémi Boutonnet, Cyril, and myself could prove is that the free Araki-Woods factors are strongly solid. And let me quickly say where this comes from and how this is done. So the point is that you build the continuous score, the cross product with the modular automorphism group. That's a to infinity factor. So if you want to apply Sorin-Popas to one deformation rigidity theory, you take a corner by a finite projection, and this fits perfectly into the theorem of Ozawa and Popa. So you would say, okay, we can deal with corners, so it's over. Well, no, there is a tiny caveat, namely, if I take these corners, the normalizer on the original level does not exactly give you normalizers on the level of the core and the corners of the core. What you get is something more general than the normalizer. It's a kind of groupoid version of the normalizer. People call it groupoid normalizer, pseudo-group normalizer. So you have to deal with a stronger version even than strong solidity, covering generalized normalizers. And that's exactly what holds even in free group factors. It also holds in the free Araki-Woods factors and their cores. So they are so-called stably strongly solid. So even all kind of pseudo-normalizers do stay amenable. And that's the last thing I wanted to tell. Thank you.
Questions? Yes.
I can make a comment on the first part of your talk.
Sure.
You associate to every standard space
Yes.
factor. Then it would be good to understand what happens when you take an inclusion standard space. You get an inclusion factor. These are, of course, infinite index. And at the first instance, one would guess that the relative commutant is trivial because every. But there are examples where the relative commutant is very big because there is an intermediate type 1 factor, split property. And this, I think, is surprising.
But not in the free case, I guess. Or
in the free case.
because when you take, but if you take the standard subspaces, how compatible is this with the modular automorphism group? So on the level of the orthogonal representation, it's not just an invariant subspace, I guess.
No, it's not an invariant subspace.
Ah, it's very much non-skewed.
Yeah,
Okay. I didn't know that.
In fact, there is this general also problem to understand, to characterize, to classify the inclusion. So you have, of course, the two modular flows, but you have also other invariants, the angles and whatever.
Yes.
So that's there is interesting problem that we don't know.
Absolutely. Yeah.
Other questions? So, what's your feeling about the bicentralizer problem?
I really feel that there is a counterexample. But if I tell that in the presence of Cyril, then he doesn't speak to me for 2 days.
But it's a function of time.
It's a function of time.
You know, 4 years ago, he would have been, very happy. Now, he says, no, I don't get it. No, that's a time, always it's a kind of time function.
Of course, there was the hope that free Araki-Woods factors with very continuous type of measures, say with the Lebesgue measure, would give you counterexamples, but that, no.
Is there, from the logical point of view, some sort of impossibility to actually classify completely all Araki-Woods factors?
No.
Well, I mean, it depends on what you mean by classify also. I mean,
Well,
for
yeah,
example, if
you
look
construct a
at the-
bijection with some sort of class of objects, probably, but anyway.
Well, I mean, I just wanted to say that, I mean, if you look at the kind of hyperfinite situation, right, I mean, the type 3 factors are classified by ergodic flows, right? So,
Yeah, we consider that as a complete classification, although ergodic flows are... No, that's perfectly acceptable, but at the same time, you have no tool to decide when two ergodic flows are the same. So
I agree. No, yeah, of course, but I was going sort of beyond that, you know. I mean, you know,
Sure.
just some
classical ingredient.
yes, some yes.
I don't think there's any obstruction
By,
as far as I know.
by countable, how do the logic say?
No, it's not classifiable by countable structures if you want to go into that. No, that follows already from here.
Yes,
Yeah.
well, of course. Yeah. Okay, so if there are no more other questions, then thank you.